Welcome to another episode of the Outsender, who is the indoors sender, as you can see. And I'm sitting indoors with a fireplace here, and it's pretty warm, nice and cozy. And well, you can see also that I'm actually indoors, whatever you call it, in this television, this old cathode ray tube television. And well, question is if I'm really indoors, or if the television is really indoors, because I have this big hole looking straight out, and you can see this pretty apocalyptic environment that I'm sitting in. And well, I thought that was fitting for this episode then. And the reason why I have this is because I'm recording this on a laptop with just a laptop camera. So I wanted to keep it a bit smaller, because it's not the quality is not that great. And I'm also doing, well, it's a laptop episode, basically then. And I'm sitting here in, this is a Swedish Army camouflage, the M90 camouflage. And, well, yeah, it's like Corona, so I'm kind of mixing up my private life with the my army, whatever. You have some personal kind of training, so it's pretty weird. And I'm out in the middle of nowhere in the forest here, so it's not like you're connected to to the ordinary society right now. And yeah, that's the situation. So I thought that was pretty fitting given this episode. And this episode is going to be about my plan to make a one-time pad encryption for that is supported by computer software. It's a computer software based one-time pad encryption that will have computer software that helps you encrypt, decrypt, and generate keys, and also generate the instructions for how to use this system. And I have chosen to call it Krypto431. And it's a one-time pad system, and where 431 is the sum of my call sign, 0 alpha 6 Mike Whiskey Alpha, in ASCII characters. Yeah, it's basically it's a sum. So a one-time pad crypto is about summing stuff and subtracting stuff. Well, encrypting by summing up stuff and decrypting by subtracting. And just a bit of background. Why do I want to do this? I have written this in I have this GitHub repository, and I'm sort of a programmer. So yeah, it's pretty common that we use GitHub or stuff like that for storing our code, and it's a version control system that keeps track of all the changes you do in code and stuff like that. So that's why it's here. But you can see, if you're familiar with this, you can see that it's a private repository. It's not public yet, and I have this work in progress branch here. So it's just started, and I also have this README file where I have described the whole system, but it's not. I made a few mistakes when I thought out how I wanted to do this from the beginning without really testing it. But now I've tested it, so I've changed a lot of stuff, and then this text is not correct anymore, basically then. But I have changed it, so now it works according to what I want to do with this. And one thing that you have with one-time pad, well, first, what is a one-time pad? It's in cryptography, it's a technique that cannot be cracked, so you cannot you cannot use cryptanalysis. Well, you can use cryptanalysis, but you will probably not be able to break it. At least not that easily, you know. So it uses just a pre-shared one-time key. One-time pre-shared key. It's a symmetric encryption, so you use the same key to encrypt as you use to decrypt. But you have to share this key to the party that should be able to decrypt it, obviously. So it has the same size or longer than the message. That's very important. Then you should never reuse some part of this key, because then it becomes vulnerable to cryptanalysis. And yeah, so there are some caveats here. Then the key must be truly random. So you need a good random number generator to be able to do this. So the key must be at least as long as the plain text, and the key must never be reused in whole or in part. And the key must be kept completely secret. So if you're getting caught, you have to eat it or burn it, I suppose. Well, maybe not eat it. I guess it depends on how close you're to danger when you eat it. I suppose some intelligence agency may get the idea that they want to carve it out of you. So before it gets dissolved by the you know, this is one-time pass was used during for agents and you know, stay behind type of activity throughout the entire 20th century, not just you know, Cold War, but Second World War, and well, I guess you know, all the way back actually. Definitely First and Second World War, especially for some kind of stay behind activity then. And this is a typical, how it will typically used. So something that you will recognize as a military radio operator is that you have groups of 5 letters. That's a typical crypto mass or ciphertext. And it can look like this. This happened to be a Diana crypto. It's a one-time pad used by the US National Security Agency. And it's codenamed Diana. And like many names here, there are 5. In Diana there are 5, and Irene, that's also 5. You may have heard that in a movie or 2. And well, in this case, it's 5 groups of 5, and that's super common. And if you practice CW, there is always like a 5 random 5 groups of 5 letters that you can practice on. And that's just the standard length, or the average length of a word in Western languages, basically, then about 5 anyway. So this is very common, and it's very convenient to send 5, because if you miss something, you can actually keep it in memory what you heard, and then the pause comes, and then you can recollect that from memory. It's not like 7, it's not 8. That would be more difficult to try to keep up with. But 5 is a really good number, and that's why it's been used throughout throughout all the Western world then, this type of crypto. So a bit of a history. Frank Miller in 1882 is supposedly the one who actually invented this one, but there was Gilbert Vernon in 1970 who acquired the patent. No, he invented he got the patent in 1919. He reinvented the whole thing in 1917, but however, he worked at Bell in AT&T Corporation, and cipher based on teleprinter technology. So he invented, I think he invented the XOR. The XOR, where does it say the XOR thing? Yeah, well, it's an operation in computers, and later it was it's a standard machine operation, the XOR thing. So I guess that's where it comes from, and it's also called the Vernon cipher. So skipping ahead then, how does it look like? And you have A to Z, so that's 25. That's 26 letters, like the English American alphabet. And you know, is it English or American? If it's there are Americans obviously. So, but it's the English alphabet, A to Z. So that's 26 letters, and it's coded that A is 0. So that's number 0, while B, Bravo, is number 1. And Charlie is number 2, etc. Then, and Hotel in this case is number 7, Echo is number 4, Lima is 11, and Oscar is 14. So that's the message then, just hello. And the key in this case is a random number, or it's randomly generated A to Z also, so it's the same thing. In this case, it's X-ray 23, Mike 12, Charlie 2, Kilo 10, Lima 11. So that's the key then, and then you add the key. You take the numbers of the message and add the key. So 7 plus 23, that's 30. But the result here is 4. So how does that work? Well, we have something called modulo 26. That means that if you have a number that is above 25, or if it's 26, then it goes back around and starts back at 0 again. So a number can never be higher than 25, then it goes back. That's at 0. So that's modulo 26. So that is employed here. So that means that 30 will go back. So you count back again to starting from 0 again, and then you end up with 4, which is echo. So the fourth or the fifth letter in the alphabet in this case, and 16, that's Quebec, and 13 November, 21 Victor, 25 Zulu. So you have Echo, Quebec, November, Victor, Zulu. And you have the cipher text here again, Echo, Quebec, November, Victor, Zulu, and minus, so you subtract again the same key. So we have X-ray, Mike, Charlie, Kilo, Lima. So you take minuses in this case. So 4 minus 23, that's minus 19. How does that end up being 7? So you use modulo 26 again, but yeah, it's like it doesn't go below 0, obviously, so it starts at 25, and you go back that way. You go back like 19 characters, and then you end up at 7 again, and that's an H. And you have the message then deciphered, hello. So that's pretty simple then, but that's only it's only A to Z. How do you make space, punctuation marks, commas, question mark, and stuff like that? And how do you make numbers? Yeah, that's where you need a system. So that's what Krypto431 is. It's a system where, first of all, how do you know which key you're going to use to decipher the message? So in this case, the first 5 letters. This is something which is true for all the Western defense type of encryption key stuff, ciphertext that you send, is that the first group, this first group that you receive, that identifies the key. This is very common. So I think it's used just about everywhere in the Western world anyway. So the first group identifies the key. So then you know that Lima, Foxtrot, November, Hotel, Yankee or something, whatever it says, that's the key. So then you go find the key. So now you know which key you're going to use to decipher it. So that's part of this system then. And it's always going to be groups of 5 letters. And well, here I explain how this works, and I'm thinking that I thought that I could use 0 in this case as like a magic extra 26th or 27th letter or number in while encoding it, but I thought completely wrong there. It was completely it was a mistake obviously, since then I found out that when I tested this I couldn't generate a Z, a Zulu, so that didn't work. And so I've since restructured this one, so I explained a little bit what modulo 26 is here. What if you want to do case sensitivity? You want to do small, what's it called, capitals and uppercase and lowercase, obviously. So what's the reason for that? And I also want to do some extra characters like equal to sign, slash, plus sign, what more? Yeah, something like that. Because I want to be able to base 64 encode the message. or I want to be able to send base64 encoded content. So you can send actually binary content. So that's the cool thing here, that I want a system that you can do completely manually, but you can send binary data. And maybe I'm not thinking about that you're going to send like an image or something, but maybe other encryption keys or passwords or tokens or whatever. And also I'm thinking in the future then that you're going to be able to send structured data, like a table of very structured data, as something called protobuf. So protobuf is a condensed format that we use as programmers for communication between APIs, or it's a more modern, compressed type of API language, not a RESTful thing where you send like JSON, you send ASCII. Basically, this is a binary format. It's a binary encoded format. So I want to be able to send protobuf because that's pretty short compared to if you want to send a whole JSON. That's pretty bloated. And you can then protobuf encode this and send it as a base64 encoded message, which then could be encoded using this Krypto431 system then. So you're going to be able to send binary data. And I explain here how I do it, and since I have changed, I don't use this anymore because it doesn't work, so I haven't changed this article yet. Keep that in mind. I'll explain a little bit later how it works. So if the message spans more than one key, what do you do then? Yeah, then I have a system to do that. Also in this whole idea then, you can actually use more than one key to encrypt your message. Also, you want to be able to do space, so you get a separation between characters and content or whatever. And here we are then, the new system. So in this system, I have two character tables. So one character table is A to Z. That's your normal 0 to 25. So it's 26 letters, and then there's an alternate character table. Skip this one. This is not correct. This is a correct one then. And I'm thinking that you can change this depending on where you are in the world. You can change the characters. So the characters I have here are 0, 1, 2, 3 to 9. So you can do numbers, where 0 is alpha then, obviously. And it's the same thing as alpha is 0. But in this case, you can encode numbers also. You can send numbers in your message. And I also have the Scandinavian characters here, O, Ä, Ö, and then Norwegian and Danish, O, Ä, Ä and Ö. So those are the Scandinavian characters. So yeah, you can do this in all of Scandinavia, and you can do the message in English also then. So what I did was took the most infrequent used characters in the English alphabet and in the Scandinavian alphabets, and used as special control characters. And in this case, you cannot write a Q. You cannot write the Quebec character. So if you have Queen, you cannot just write Queen. You have to encode the Q. And and then you do that like that. So Z in this case, it means that you're going to change to the alternate character table. And when you change to the alternate character table, you also have Z here. That means that you're going to change to the primary character table again. So Z is used to switch between the character tables. And Q in the primary character table is used to make a space. And it's the same thing in the alternate character table. Q is not used to make a space, but is used to make a Q. So that's how it's encoded then. And the same thing with Z, but I cannot use Z here to make a Z. So in that case, I just, you send Zulu Sierra. That's a Z in this system. It's a double character. It's encoded to fit in the modulo 26. 1 to 26 letter thing here then. So we only use these letters to send your message, basically then. So you will never see these in the text you're going to encrypt, and you will never see these characters in the ciphertext. So that's why you need to have some system to encode them differently. And so we have these 2 character tables, and with these characters you can make the base 64 characters that are necessary to generate those. And in this case, X-ray here, CL, that means caps lock. So I'm just thinking that it will act like a caps lock. You change between uppercase and lowercase, basically, and that's also necessary to be able to make base 64 encoded content then. And as I said, Z is used to change back to the primary character table in this one. You also have something called change key here, and that is what follows. That means that it means that you're going to message spans several keys, so you change to another key there. So yeah, that's how that thought is. So that means that well, here it says 0 again. This is wrong. So we need to go down to the new idea here. So that is true modulo 26, and that means 0 to 25. So the rule is that 0 is only to switch between tables, and it cannot be used as a Zulu sign in, as a character Zulu in either table. So what do you do to be able to make a Zulu then? Well, you have to first change character table and then make a Sierra, and that's a Zulu. So, like I said here, up here. So Zulu here, that's a Sierra in the encoded form then, in the second character table. So just an example here. This is a secret text. How are you doing? Take care. Bye. So with Zulu, at first I thought that we're not going to use Quebec as a space, but Zulu, Romeo, Zulu was to be used as a space then, and then obviously if you use Quebec as a space, then you see that is a shorter message, 3 groups shorter than if you would use Zulu, Romeo, Zulu as a space. So yeah, the space is pretty frequent, so I'm thinking that should be 1 character. How do you then do with queens, cobras, and zebras? That message then. The queen, that will be Zulu, Quebec, and then you change back to the primary character table, and then you just continue queen, and these are all arranged in groups of 5 obviously, so that's why we have the space here. And queens, and then we have a comma. The comma is a Zulu whiskey, and then we change back Zulu, and then Quebec, that's a space, and cobras is just cobras, and then we have a space, Quebec again, and the space again, zebras. Then you cannot write zebras, so you have to write Zulu, Sierra, Zulu, that's zebra, and zebras, and then Zulu, punctuation mark, P there. I took Papa as punctuation mark, so you know that. Basically remember that as a dot then, as a punctuation mark. And then we have some Z's here. So you just fill up the whole group. So you always end up with the last. You have to do some filler here to fill up, so you get to a 5-letter group, and you fill it up just by changing back and forth through the character tables, Zulu, 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 until you reach a full group. So that's pretty simple. Even if you're tired and decoding it, you're just changing back and forth the tables, and then you run out. Okay, what now? So then you don't write anything extra there. So that's one idea. Then we have some Swedish here. How do you say that in military English? go to waypoint 79 or rendezvous point 79 in this case. So you can see that it becomes longer than the actual message then. So that's the problem, obviously, since we only use 26 characters here, and we're going to encode space and numbers and Swedish signs here. It would obviously become longer then. But as you can see, it's not that long. It's not, and you see that it's filled with 3 sets there. It's not that long, actually. And also, I have the idea that you should not only be tied to be able to use this with a computer. If you don't have a computer and you need to generate a key, how do you do that? So then I figured out that you can use dice, obviously. It becomes pretty good in randomization. And if you have 5 dice that you can generate a number from 1 to 6, which is a normal square dice, generates random numbers from 1 to 6. If you have 1, you can throw it 5 times, and that's your first character in the key. But if you have 5 dice, it becomes a lot easier. You just roll all dice and add all the numbers together. But then the lowest number you can generate is 6. So, no, sorry. The lowest number you can generate is 5. What if you want to generate a number between 0 and 25 then? The highest number you can generate is 30. So, you can see here then, if you take -5, then you can generate a number between 0 and 25, which is exactly what we want then. So that's perfect. So, in this case, you can see that it's 1 to 26. This is I had the idea that it would be possible to use 0 outside of the modulo 26, but that's not possible. So in this case, this is not correct. I'm going to change that to 0 to 25, obviously. And it says subtract 4, but it will be subtract 5, obviously, to generate 0 to 25 instead of 1 to 26. Yeah, so here's 431. It's my cosine, and the sum of it is 431. I just had some stuff there, bash stuff. But the language that I will do this in is going to be Golang. I've already started with some stuff here. And so if you're interested in this crypto system and you do some Golang programming, you're very welcome to contact me, and maybe we can work together with this project. That would be pretty cool then. If you're also interested in this project but do coding in some other language, then you're also very welcome, because it would be super cool to have several different options in several different programming languages to be able to use this system in then. So what I'm thinking, first and foremost, is that the system the binaries that you generate with this one, and Golang is pretty nice because you can generate binaries that you can distribute. You just have a single binary for the whole system, and you can pretty much distribute it then. However, it needs to be compiled for the target environment, so that's important then. And I'm a Unix or Linux programmer primarily, and I haven't done any Windows programming for many years, so I have no idea how that works. However, you can generate Windows binaries with Golang, no problem. The directory structure is different, so if you are a Golang Windows programmer, that would be super cool to work together with this, to have the same code base, so you can use that easily for both systems, Windows and Linux then. And we would obviously put out releases, so you don't have to compile this yourself. You can just download the binary releases and use them. And in that package, there will be multiple binaries for all kinds of operating environments, target environments then. So that would be the use case, and it would generate, I think it would primarily generate PDF files and text files. So it would generate both, that you can print then with keys and instructions how to use the system, so you get some help then. And primarily the keys and the instructions for using it. That would be, I think every key would have the instructions on them or something like that. So it would be useful from a UI or UX perspective, I suppose. And so you can actually use it pretty easily then. Because that's the problem with, one-thumb pads. It's pretty simple, but how do you actually do it when you transmit something? Now we enter the world of how do you then, if you're an amateur radio operator and you want to practice this stuff, how do you do that? Well, unfortunately, unless you're in Sweden, and with the Swedish Broadcasting Agency, they have confirmed or said that it's completely fine if you send encrypted content. We don't care about what content you send, as long as you identify who you are when you're transmitting. So that's the Swedish Broadcasting Agency, but I know that in many other countries, the Broadcasting Agency has forbidden amateur radio operators to send encrypted content. That becomes a problem if you want to practice this as an amateur radio operator. And maybe you have like a volunteer organization or something, a civil defense organization where you can join and practice this stuff. Because that's what I've been talking about in a Swedish version of this video, that it's very good if you actually train the exact same thing. Because if in a civil defense or in a total defense perspective, you would eventually end up being, coordinating or communicating with a military radio operator. Since it's a, combined effort, civil defense and military defense combined in a total defense effort. So that would be one highly likely scenario in my part of the world anyway. So yeah, if you're an amateur radio operator and you obviously get in touch with a military radio operator and you have a certain procedure that you're not familiar with, you have to practice that before actually, using it. Otherwise, the military radio operator may be a bit, not angry, but some military radio operators are very strict with the radio procedure. So that's one caveat. And so if you're an amateur radio operator and you cannot deal with that, there's some friction possibly. I'm not talking about myself here. I'm pretty open and like that. But if you ever listen to military radio operators who know their stuff, this communication can be super fast and efficient, especially then with crypto information, which can be pretty, long then. And it has to be very correct. If you don't want to send the wrong crypto stuff and then someone deciphers a message and figures out that there's something wrong here, I can't decipher it. So that's not really an option, especially not with the manual encryption. And if you use a computer and send messages, and fine, just send it again. But in this case, it's supposed to be sent manually as a last resort type of system then. So I don't know how you would do that in another country then, where you're not allowed as an amateur radio operator to send encrypted content. We are very fortunate here that we are allowed to do that, because that means that amateur radio operators can practice exactly the same radio procedure as military radio operators use. So there would be, if you practice it and you do it, actually, you have to do that obviously, then there would be no friction and it would flow pretty efficiently, this type of communication. And also the groups of 5 and everything that's used throughout, it's been used for ages, in the western part of the world anyway. As far as I know, I don't know how you do it in other languages, but in the western world, that's how we do it. So it will match, if you do this, it will match and it will be familiar with possible military encryption that is actually used, a more advanced one that you use computers, for example, or these special crypto devices that you can have to encrypt and decrypt messages. Something like that anyway. So if you like this video, please give it a thumbs up and consider subscribing. And please visit my Patreon page at www.patreon.com/outsender and consider becoming a patron. I appreciate that a lot, and that motivates me to do stuff like this, for example, then. So, do that. And if you're interested in cooperating with this project, you're a programmer, or maybe you have enough programming skills to be able to do this, then You're more than welcome to contact me either in the comment section below or wherever, however we can hook up, or you can go into the About page on this channel and scroll down to what's it called, Business Contact, or Business Inquiries or something like that. And you click that to reveal my email address, and the email address is Sierra Alpha 6 Mike Whiskey Alpha at Radio Horizon, Radio Horizon T.se .Sierra Echo. So yeah, that's how it is. And yeah, take care, and I'll see you in the next one. 73, end of message, out.